Veeravalli is at the University of Illinois at Urbana-Champaign. He received his PhD from Illinois and then went on to Cornell, and he's now back at Illinois like most people from Illinois. They like to go back home.
Right. No, they like to leave actually.
Right. So he's with the National Science Foundation here on a 2-year. This is second year there. He's won a number of awards, including the IEEE Browser Thompson Best Paper Award and the PCASE Award, the Presidential Early Career Award for Scientists and Engineers. His research interests are in multi-user communication, sensor networks, estimation, detection theory, information theory. And today he's going to talk about some new results on MIMO processing. Thank you.
Okay, so this is a talk on a somewhat old problem now. I mean, I guess MIMO has been around for 5 or 7 years, and it's been a lot of work. And so I'll give this old problem a new twist. Hopefully, you'll be convinced that it's a new twist. This is actually joint work with one of my students, Ying-Bin. Actually, she goes by Grace Liang, who's actually finishing her PhD this coming summer. So, you know, she's going to be looking for faculty positions. So if there are any positions here, keep her in mind. Akbar Saeed actually is a professor at Wisconsin who, Akbar and I overlapped at Illinois when we were students. And he actually, it turns out, he was a student in a class that I taught at Illinois in '92 when I was finishing on my PhD. So he's also my student in some sense. So this is. How many of you haven't seen the MIMO channel model? Only one hand. So this is a familiar model to many of you. You have NT transmit antennas here, except for these symbols. It's NT and NR, that I use here. People use all kinds of other symbols, M and N and so on and so forth. Other than that, this model is a pretty standard model. NT transmit antennas, NR receive antennas, and there's the channel matrix that connects them. And we're going to look at a situation of flat fading. This is the simplest model for fading, so non-frequency selective fading. And we're going to look at the channel over one symbol period with the assumption, of course, that the variation from one symbol to the next is stationary and ergodic. So we can focus on one symbol period. And Y is the output, X is the input, W is additive Gaussian noise, H is the channel matrix. And here, this gamma represents a signal-to-noise ratio at each receive antenna. And in order for that to happen, we need to normalize things. So we have an input power constraint so that basically one per transmit antenna. And we normalize the channel variances so that basically gamma then represents the receive signal-to-noise ratio. Okay? And we have additive noise. That's W. Okay, so that's the model. And we're interested in finding the capacity for this channel. Okay, and this is actually, as I said, an old problem. But the twist that we're going to add to this problem is we're going to allow for a very general model for H. Okay? So here's what I'm going to assume about H. Elements of H are proper complex. Identically distributed, of course, there's the far field assumption. So we assume that the arrays are far apart, so that if I look at any pairs of transmit and receive antennas, they basically see, statistically they see the same channel. So they basically can't distinguish in that sense, but of course they could be correlated. Okay, so they're identically distributed, correlated. We normalize their variances to 1, like I said before. We don't necessarily assume a Gaussian model. We could possibly have a deterministic line of sight component. So basically, in addition to reflections from obstructions, there could be a direct line of sight component that joins these two, and that's typically modeled as deterministic, not random. And The other assumption we make about H, and we'll actually talk about why these assumptions are actually reasonable in practice, is that H has the same distribution as minus H. This is a simple symmetry assumption. And something that satisfies all these properties is something that looks like this. If each element is a summation of a bunch of paths with basic complex numbers, basically, with deterministic coefficients beta, but uniform random phases phi. Okay, if you look at the statistics of this, it satisfies these symmetry properties. If I remove this minor side component, it's deterministic, and of course, it's proper complex. Okay, so this is basically I would say the most general model you can have for H for any scattering environment. We'll assume that H is known at the receiver, and the statistics of H are known at the transmitter. And actually, we'll talk about what we need to know about H at the transmitter a little bit later. Okay. For now, assume the statistics are known. So basically, there's some joint distribution for these elements of H, and that's known. And the questions we ask is, what's the ergodic capacity of this channel? Okay. And what's the corresponding optimum input distribution? And then we look at asymptotics as the number of antennas go to infinity. All right, so let me talk about the history of this problem. This problem was first solved by Teletar, actually much earlier than this 99 date that he has on his paper. So I think it was the mid-90s sometime, 95 or so, when he was Bell Labs. And basically looked at the capacity of the IID Gaussian model, where the elements of H are zero mean complex Gaussian random variables and independent. Okay, and actually asymptotics for a large number of antennas was also studied by Teletar. We actually found a closed form expression for the asymptotic capacity, and these asymptotics were shown to be very accurate even for 3 or 4 antennas by Comet and Hughes a little bit later. So that's the IID model, IID Gaussian model. A correlated Gaussian model was also studied by several people, starting with Vysotsky and Mahler for the case where you have multiple transmit and one receive antenna. And there, basically, the idea was the key results that they had was basically how do you characterize the optimum input in this situation and this correlation. And basically, they also showed that for large correlation, actually, beamforming is optimum. Beamforming in one direction basically turns out to be optimum. One-dimensional signal turns out to be optimum when things are correlated. So there's been a lot of work on that. But again, for the Gaussian model again, and actually asymptotics for this Gaussian model also was studied by Chua and Shea and other people. Okay. But common to all of these papers is the so-called product form correlation model. Okay, the way you assume that if you look at the correlation for transmit antenna, I guess I'm using K for receive and L for transmit here. So transmit antenna L and receive antenna K, and if you look at P and Q for the other pair, the correlation between these two can be written as a product of a transmit correlation and a receive correlation. Okay, I think there's something wrong with these subscripts here. There should be an L and a K rather than an I and a J. Basically, the idea is that I can write the correlation between these elements of H as a product of a transmit correlation and a receive correlation. And this is actually a pretty restrictive assumption, okay, except in some very special scenarios. And we'll actually talk about what this means physically a little bit later. Okay? But it's crucial to a lot of the analysis that we've done. Okay, so we're going to drop all of those assumptions and only keep the assumptions I had earlier. So we don't assume Gaussianity, we don't assume this correlation structure, and so on. So the key to doing the analysis in the general case turns out to be this so-called virtual representation of the channel. And this was something that was introduced by Saeed, and that's how I ended up collaborating with this work. So, so the idea is let's look at the physical representation of the channel first. So the channel is formed by a bunch of paths that can connect the transmitter and the receiver. Okay, and these phis represents the angles made by each path, basically, the transmitter here and the receiver here. It's a bunch of scatterers that could actually cause different paths to connect the transmitter and the receiver. So you can write the channel matrix H in terms of these individual paths by essentially summing them up. Okay, here I have a finite discrete sum, but we'll talk about generalizing into a continuous case in the next slide. So you have a bunch of paths, and you can actually look at the gains associated with each of these paths. The beta I as essentially the real gains associated with the path, and this is basically the memory initial unknown phase associated with each of these paths. Okay, and these AR and AT are the so-called steering. What are they called? Steering and steering and response vectors. Array steering and response vectors. That's from the array processing terminology. So, in fact, what you can do is basically these thetas are really related to the physical angles phi in this fashion here. Okay, so D is the spacing between the antennas, lambda is the wavelength, and phi sits inside here. And basically, this theta variable captures the physical angles. All you need to know about the physical angles made to by each of these paths of the transmitter and receiver. And if you plug these vectors in, basically you can express the channel matrix in terms of each of the paths, the summation. Okay, and this is not that hard to do. This is basic physics. You're just looking at the phases and the gains along each of the paths, adding them up, and there may be a separate piece associated with a line of sight path that connects the transmitter and receiver directly. Okay, so that's writing H in terms of the physical paths. Okay, you can actually get a continuum path model. So each of these scatterers in a real environment is really going to produce not just one path but a continuum of paths. Because no reflector in the real world is going to be perfectly smooth. Okay, so really a more correct model will basically replace the discrete summation that I had in the previous slide by a continuous set of paths, and that's this model basically. And basically what I have is I've captured the gains and phases of the paths in this function alpha, which is like a density of path gains as a function of transmit and receive angles. Okay. And the line of sight path, of course, it could be a discrete path that sits outside all of this stuff. Okay. And this alpha, which captures basically the path gains and phases as a function of angle, is called the angular spreading function. And remember that when I talk about angle, this theta variable is related to the physical angle in this fashion. It behaves like an angle variable in the sense that it doesn't matter if I go outside the interval 0, 1, I can map it back to 0, 1, and it still doesn't affect how I represent H in terms of those angles. But remember that every physical angle phi could correspond to more than one, every angle theta could correspond to more than one physical angle phi, except in the case where I have less than half wavelength spacing. Okay, so if my wavelength spacing is less than half, okay, then basically I have a one-to-one mapping between the physical angle and this so-called virtual angle. Okay, otherwise you think about more than one angle possibly corresponding to each theta. And so this will be important later. When I talk about beamforming, I'll talk about beamforming along specific thetas, and each theta may correspond to more than one physical angle. Okay, if the spacing between the antennas is more than half wavelength. Okay. All right. So now, in this representation of the channel in terms of the paths, I've inherently assumed that I can resolve paths up to any degree of accuracy I want in angle. Okay. by writing H in terms of each of these paths, I'm inherently assuming that I can actually distinguish between each path that connects the transmitter and the receiver. But if you look at any a finite array, okay, it's going to have a finite spatial resolution. So this array cannot distinguish between angles that are spaced more than 1 over nt apart at the transmitter and 1 over nr at the receiver. So basically, I should be able to write down this H actually in terms of a finite number of equivalent paths, or rather I should be able to replace a double integral by essentially a double summation, okay, with fixed angles at the transmitter and at the receiver. Okay. So in fact, that's all I've done here. I've looked at angles that are actually essentially in fixed directions that are equally spaced at the transmitter and receiver, okay, and basically written this double integral here and the double summation. Okay. And in fact, it turns out, it's not that hard to see, that with the equal spacing like this, these matrices that I have to pre and post multiply with, okay, turn out to be just Fourier transform matrices, spatial Fourier transform matrices. And so what I really have is a representation for H in terms of this another matrix H tilde, okay, which essentially captures the gains along each of these cones, okay, at the transmitter and receiver. And these are unitary matrices, so I can go from one way to the other very easily. I can pre multiply by AR inverse and post multiply by AT inverse. On the other side, I get back H tilde from H. Okay. So remember, actually, even though I gave you this physical interpretation of equally spacing paths and or equally spaced paths on the transmit and receive side, I could have written H in terms of some other H tilde with any unitary matrices here. Okay. Any unitary matrix AR and some other unitary matrix AT could have given me some representation for H in terms of some H tilde. It will turn out that this specific representation using these discrete Fourier transform matrices give us some special properties for H tilde, okay, which we're going to exploit. And that's what power of the virtual representation. And so that's what we're going to examine now. What do I get from actually using AR and AT to represent my channel? Well, it turns out that the elements of H tilde, and again from this physical representation, elements of H tilde basically have contributions of paths that lie in these cones. The first element comes from this cone here and this cone here. Okay, all the paths that lie in those two cones add up to produce the first element of H tilde, roughly speaking. There'll be some overlap. You know, there's sinc functions that basically spread things out a little bit, but roughly speaking, that's what's going on. So roughly, by adding up all the paths within these cones, okay, I get the elements of H tilde. Okay, and basically, I have some kind of path partitioning going on. Of the paths that connect the transmitter and receiver can be partitioned into these cones, and each of the cones have a separate set of paths. And the advantage of that is that since a different set of paths contributes to each cone, the elements of H tilde will be roughly independent if the phases of those paths are independent. So if we make the assumptions that the phases of the paths all the paths joining the transmitter and receiver are independent and uniform on 0 to pi, which is a standard assumption that's made, it goes back to Bellow in the 1960s, and it's a reasonable assumption, then the elements of H tilde are independent. The other thing you get is if the phases are IID uniform 0 to pi, then you can easily show that this has to be a proper complex random variable. Okay, by proper complex, it means its pseudo covariance is 0. I mean, you should have studied this in your first course in graduate level course in communications.
Excuse me, is the double thing its approximation.
Yes, this is an approximation. So basically, it gets better and better when you have more antennas for this partitioning. But we're going to take this approximation and assume that it's exact, and assume that the elements of H are independent.
That's what I was getting at. Which properties are with the approximation?
Yes. Yes. And of course, I mean, the question is, is this a better approximation than assuming that they are IID Gaussian? And I think this is a much better approximation because that is visible justification. So what we are saying is that even though the elements of H may be correlated and non-Gaussian, the elements of H tilde are going to be roughly independent and proper. And also they have a symmetry, and the symmetry just follows from the random phases. That if I replace H by minus H, actually it's symmetric around 0 again. You can go in any angle you like. You get the same distribution. And that's basically the circular symmetry associated with these kinds of random variables. Just put any random phase to this stuff and it doesn't really affect the distribution. And we'll exploit this property too in our analysis. Okay, so that's the that we talked about the independence of H tilde. Now let's actually study the distribution in a little more detail. We need to actually say something about the marginals. Okay. Now we can say something about not the marginals, but something about the variances through what's called the scattering function. So let's look at that. So again, the independent uniform phases gives us what's called uncorrelated scattering. Okay. Now with uncorrelated scattering, there's an associated scattering function. So if I look at basically the angular spreading function at angles theta r, theta t, and then theta r, theta t prime, and look at the correlation, then I get a delta function because of the independence of the phases, and then the power gain associated with those angles. Okay, and so basically, what is the scattering function? The scattering function basically captures power, how power is distributed in the channel, or gain is distributed in the channel as a function of transmit angle and receive angle. And in particular, if I have a scattering environment that looks like this, with a blob here and a blob here, then the corresponding scattering function is going to look something like this. So there's a large angle associated with, let's see, this is the transmit axis. So I've distinguished these blobs in the transmit direction. And in the receive direction, I have this one making, one of them has a large cone, this one has a large cone, and this one has a small cone. So that's what it would correspond to. And the scattering function, of course, is normalized because our variances are normalized, and so it integrates to 1. So this is similar to the scattering function in time frequency that was introduced by Bellow a while ago. Okay, so now let's look at this, how the scattering function is related to the H tildes. What we can show, what we know from before now is that the H tildes the elements of H tilde are approximately independent. And so let's look at the variances of these coefficients. It turns out that the variances are approximately samples of the scattering function. That's not that hard to show. It's basically a sinc interpolation kind of idea. Okay, so if I have a scattering function that looks like this, the variances of the coefficients are simply samples of the scattering function at these points. Okay. Basically, uniform sampling in the theta t and the theta r directions. And with our normalization of a scattering function, our variance is also normalized to sum to nt times nr, and that makes sense. We have a Fourier transform representation. In the original domain, each element had variance 1. The sum of the variances is nt times nr. In the virtual domain, the sum of the variances is also nt times nr. So, how do you capture correlation in H? Well, correlation in H is captured in the variation in this variance matrix. Okay, if I have something that's uniformly spread out, okay, or a scattering function that's uniform, then these variances are approximately going to be equal, and then I basically have something that's roughly independent in the original domain, or uncorrelated in the original domain. Okay, and if there are small blobs here, and there lots of zeros in the variance matrix, then I'm going to have large correlations in the original domain. Okay, does that make sense? Okay, so now let's go back and look at this product form correlation assumption that was made in a lot of other work. It turns out that you get this product form correlation only if the scattering function is also in product form. Okay, and that's not that hard to show, and intuitively it should make sense. And so what does that mean? I mean, if you look at this typical scattering function, it's going to be hard to make it look like it's in product form. In typical scattering functions, you're going to have, in order for it to be in product form, you need to have basically rectangular looking blobs in the scattering function that are disjoint. Okay. And it's, in any real scattering environment, it's going to be hard to see something like that. There are some exceptions. You can have scenarios where the scattering is, say, locally rich at the receiver or at the transmitter, in which case you might end up with one large blob either covering this way or this way, and then you have something that's roughly in product form. But in most reasonable scattering environments, that's not going to hold. Okay. All right. So that's all I have to say about channel modeling. Now we're going to use this model to look at the capacity of the channel. Okay. So any questions about the model before we go ahead?
Yeah, one question. That product form, how far from the product form is it typically in practice? If we
so there have been some measurements by people in, I think there's a group in Austria that's done some measurements on the stuff and showed that the product form correlation is really not very valid in practice. And in fact, they validated something like the virtual representation. That validated the fact that in the virtual domain you do see roughly independent coefficients. So I think the independence of the virtual coefficients is a much better assumption than the product form assumption. That much we can say. They're both approximations, but I think the approximation we have is much better. And the other advantage is that the virtual representation doesn't require assumptions like Gaussianity. So now let's look at the capacity. So the capacity for this channel is actually not that hard to write down, at least an expression for it. Okay. And in fact, it can be shown that no matter what the statistics of H are, as long as you know H is the receiver, the optimum input distribution is actually a zero mean Popper complex vector. And that vector, of course, has to satisfy the power constraint. So the trace of the covariance matrix has to be less than anything. So I actually, once the input is Gaussian, you can very easily write down the mutual information between the input and output. And this is the expression of the mutual information. Okay, very similar to what you see in the single CISO case, single antenna case. And you have to maximize that now over this covariance matrix Q. And so basically the problem of finding the capacity boils down to finding this optimum Q. Okay. So we can actually, using the virtual representation, we can write down this problem in the virtual domain. Okay. So what we do is basically transform the input by AT, transform the output by AR, and once we do that, basically H gets transformed by AT and AR to give me an H tilde, and I have an equivalent representation in terms of these virtual inputs, virtual outputs, and virtual matrix. Okay. Now the problem is still very similar. The additive noise is still zero mean complex Gaussian in the virtual domain because these unitary things don't change the nature of that. So you still have a very similar problem, except now all these quantities are replaced by corresponding things with tildes. Okay. So the equation looks very similar to this, except now H tilde has some nice properties. H tilde has independent elements. Okay, and that turns out to be convenient for analysis. And so the first result, again, which is not that hard to show. Actually, this optimization is a convex optimization problem, Okay, so you can actually, it is convenient for analysis. What we can show, even if we can't find the actual optimum distribution in closed form, is you can show that the optimum distribution, as long as the elements of H are independent, is a diagonal matrix. Okay, and this is an interesting result. It says that basically the signals that you send along different virtual angles or transmit angles are independent. Okay, and if so, you allocate power according to these transmit angles, and the optimum lambda i's are easily found numerically because this is a nice convex optimization problem. So this is the first result actually. So basically, you wouldn't get such a simple result without the independence here. Okay, so that's a nice thing about looking at it in the virtual domain. Okay, and of course, once you find the optimum input distribution, which is diagonal, in the original domain, of course, you just transform the thing and you get the covariance in the original domain, okay, which may not be diagonal. Okay, that's a nice result, but we can actually look at this a little further. What it turns out that at sufficiently low SNR, and this is similar to some results which were obtained in the Gaussian case before. At sufficiently low SNR, only one element of this diagonal matrix is not zero. That means beamforming to one of these angles is optimal. One of these virtual angles, which may correspond to more than one real angle, but it's beamforming one virtual direction theta is optimal. Okay, and this is a very interesting result, and actually we'll examine this more closely in numerical result. And this actually makes things very simple at the transmitter. Okay, it's one-dimensional signal network to the transmitter. Also, you can find necessary and sufficient conditions for beamforming to be optimum in terms of just the variances. You don't need to know the joint distribution of the coefficients. Okay. So, as long as beamforming is optimum, okay, finding which direction to beamform to can be found only based on the variances. And in fact, these theorems now just formalize those results. This basically says that low SNR, you pick the direction corresponding to the largest column of this V matrix, okay, in terms of sum, and that's the angle to which you need to beamform to. And the other thing is conditions for beamforming. So what's the SNR below which beamforming becomes optimum, and that's given by this condition. Again, notice that all I want you to note here is that these conditions only depend on the variances.
So there's actually a threshold below which it's optimal?
Yeah, there's a threshold below which beamforming is optimal. So let's look at an example to see what happens for something that might be close to what might happen in the real world. Okay, so here, this is a situation. This is a highly correlated channel. Okay, there's one direction that's dominant. So there's a scatterer sitting in this direction with a large variance associated with these coefficients. And there are some other little guys, along the diagonal here. Okay, so this is a correlated channel, and let's look at the capacity for this channel. So here I have three curves here. One is the blue curve is basically the capacity of the channel because I have optimum inputs. Okay, I've also drawn here what I would get for the mutual information if I used the beamforming input, and I beamform to the best angle, no matter what the SNR is. So I beamform to this angle because it has the largest variance sum. And the other curve here is what if I ignored all the information about correlation and just sent IID inputs channel, which would be optimum if I had IID elements for the matrix. And you see here that for this example, actually I think I have the threshold SNR. The threshold SNR turns out to be 0.29 dB, below which beamforming is actually optimal. But even up to 5 dB or so, beamforming is close to optimal. Okay, that's a reasonable SNR. I mean, that's something that you could easily have. I mean, in fact, that might be too high in many outdoor wireless scenarios per receive antenna. The other thing you notice here is that IID inputs eventually become optimal for very high SNRs. Okay? And that also makes sense because basically at high enough SNRs, as long as there is some power, it's some gain in every direction. Okay, basically there's some water filling kind of argument that sets in, that basically eventually you have such a large water level that you can't distinguish between the powers that you send on each of the transmit antennas, and that's what's happening here. Okay, but at low SNRs you actually do put all your power into one angle. Now the other interesting question here is, if you've studied this stuff or looked at papers on MIMO channels, one thing that people seem to think is that the IID channel is somehow the best channel. You get the most out of an IID channel, the most diversity and the most multiplexing gain and so on and so forth. That's not necessarily the case. It really depends on the SNR. And here, we plot the capacity of the correlated channel versus the IID channel. We normalize both channels to have variance one for the coefficients. You see that below 2 dB here, the correlated channel can actually have better capacity. Okay? And basically what this is saying is that in order to get the gains, the multiplexing gains from the IID channel and create these parallel pipes over which to send information, you really need to go to very high SNRs. The other thing to note is that below this 2 dB, basically beamforming is close to optimum also. So you can get all the gains you can just by beamforming, and that's better than having an IID channel. Yeah, that's what I'm saying words there. So let's actually make some more comments about beamforming. So beamforming to the best angle can be close to optimum even for moderate SNRs. So that's something, we need to question space-time coding for outdoor environments where things might be very correlated. The other nice thing about beamforming is that you can actually find the best angle just based on the variances. You don't need the joint distribution. The other thing is if you're just interested in beamforming to one angle, finding the best angle at the transmitter just requires log nt bits. Okay, you don't need to send any more information. You can estimate things at the receiver and just send back the best angle to transmit at. Okay? And for this reason, beamforming may be more robust to errors in channel estimation of the receiver. So even if it's not the optimum thing to do, it might actually turn out to be the better thing to do in practice because it'll be a lot more robust, as long as there is a dominant angle. Yeah.
I can't remember this was if you had H with the IID components, then even at low SNR there is no beamforming, right?
Yeah, at low SNR, I mean, as long as if you can't distinguish, then
that's right.
But as long as there's one dominant angle at low enough SNR, it's going to transmit to that angle. Yeah.
How to find the threshold under which the beamforming is optimal or better than just sending IID inputs? I mean,
well, all you can say is the threshold and SNR below which beamforming is optimum. Comparing with the IID inputs, comparing with the IID channel, that's a harder thing to do, I think, analytically.
So,
I'm not sure how to do
so
that.
just by numerical, I mean.
Yeah, this example I just showed numerically that was the case, yeah.
No, I mean, he's asking, you have a formula for the threshold.
Oh yeah, formula for the threshold, but I think he's asking how does it compare to the IID channel? Whether it would have a better capacity than the IID channel.
No, he's asking the formula.
Oh, the formula, yeah, we don't have a formula actually. I just showed that in this one. This is the formula. It's written in a slightly funny way, but this is a threshold on gamma below which beamforming is optimal.
This is all because in that context you have formulas.
Which context?
What you just discussed.
Yeah, yes.
But is it in the MIMO community, is it a folk theorem that if you are at low SNR, beamforming is always optimal?
Yeah. I mean, that's a folk theorem, and we're quantifying that. I'm saying that for correlated channels, we can actually find a threshold.
Could you in fact prove this in general?
We proved it pretty generally here.
If you make some assumptions.
Well, the assumptions are, I think, pretty reasonable. the only assumption we make is that the elements of H are independent. H tilde, sorry.
Yeah, but then you could make an argument that perhaps the conjecture of the Fock theorem is true because of the structural assumptions that you made.
Yeah. Well, no, actually, yeah. So if you could generalize it. Okay. Without, so if you don't have uniform linear arrays and so on, like we have assumed, you could generalize it and just and think about sending along the appropriate eigenfunctions of the channel at the transmitter and receiver, and then you will indeed get in the uncorrelated elements for H.
But for that, you need to know the exact formula.
Well, you don't need to know. You can show that beamforming will be optimal. Threshold might be hard to obtain. Prove. Yeah, you could generalize this result, but it won't be as useful because, again, it doesn't have the physical interpretation in terms of angles anymore. Those eigenfunctions could be anything. In the virtual representation, the eigenfunctions are just your Fourier basis.
Then I go back to my earlier point. Had I start with an arbitrary A.
Yeah, you can start with an arbitrary H and arbitrary correlation. You still need to make the assumption that they're Gaussian so that when you transform things, you get something that's uncorrelated, which is also independent, and then things will work out. But the simplicity of this representation is that you get independence without Gaussianity. Okay, so actually in the last 10 minutes that I have, let's talk a little bit about asymptotics. Okay. So again, so we're going to look at asymptotics as the number of antennas go to infinity. And the reason for looking at this is that you can actually get analytical expressions for the capacity in this case, instead of having to rely on numerical. Well, I guess it's still you still require numerical techniques to solve those equations, as you see. But you get an expression that's better than just writing an expectation like this. Let me put it that way. We can get rid of this expectation in the limit. And actually, I've got rid of the expectation even before taking the limit. That I shouldn't have done. There should be an E here. So we normalize this capacity with the number n here, and for simplicity, I let the number of transmit and receive antennas equal n. By the way, throughout the talk, I made the assumption that there was no line of sight component because I didn't really talk about the line of sight component. So things get a little messy when there's a line of sight component, but it's not. It's pretty straightforward, and so a paper that we have actually addresses that scenario as well. Okay. So here, basically, they are just zero main components. So H tilde has zero main independent components, like we had for the previous results. Okay. Now, for any reasonable channel matrix H tilde, the capacity will grow with the number of antennas, because actually, as you let the number of receive antennas grow, at least in the model that we have here, may not hold in practice necessarily, the amount of energy we collect actually keeps going up. Okay. So we normalize that channel capacity by n and look at how the capacity scales as a function of n through this C bar. Okay. And we look at C bar in the limit as n goes to infinity. And the key quantity to determine the asymptotic value for C bar is going to be the eigenvalue distribution of this matrix here. Okay. And intuitively, that's clear. It makes sense that basically somehow the eigenvalues of this matrix would play a role in determining this log head function, right? And in the limit, of course, those eigenvalues go to a continuous function called the eigenvalue distribution, and this eigenvalue distribution will then play a role in determining what the C bar is. And in the IID Gaussian case, okay, when basically the elements of H tilde are also going to be IID zero mean Gaussian, it's relatively easy to compute this function, and this was done by Telegar. And we use the so-called Wishart distribution here to get the answer. Okay, so if you don't have the IID Gaussian assumption, okay, then it's actually a hard problem, especially if you look at it in the original domain. But in the virtual domain, the independence of the elements here and the fact that the optimum distribution is diagonal allows us to apply a powerful result by Goto, okay, to get the necessary eigenvalue distribution. Okay, so two things are key to applying Gurko's result. One, the independence of H tilde and the fact that I have a diagonal matrix sitting in the middle here. Okay, and so I'm not going to go over the details here. We need to make some smoothness assumptions about the input which are reasonable. In other words, the input distribution goes to something that's nice and smooth. And basically the other thing, piece of math I need to introduce is something called the Stills transform. So characterizing the eigenvalues of this limiting matrix is better done through something called the Stills transform of the matrix, and that's given by this expression here. Okay. And so if I can say something about the Stills transform, that's enough to characterize the capacity. And that's what I have here. So this first result says that if I can find the Stills transform, the limiting Stills transform of this matrix, then I can write the capacity in terms of that Stills transform. And this is not that hard to do. This is a similar result to what was done for large CDMA systems before, okay, using random matrix results. Okay, so the key then becomes finding the Stills transform of this limiting matrix, and that's what Gurko lets me do. Okay, and Gurko gives me the Stills transform in terms of, actually this seems like a complicated equation, but it's pretty easy to solve numerically. So I can write it in terms of this function E, and this E is then written directly in terms of the scattering function psi. So what's happening? So I said before that the variance matrix was formed by sampling the scattering function. Okay. As I let the number of antennas go to infinity, I get basically a continuous sampling of the scattering function. So the variances become the scattering function in the limit, and basically my answer then just depends on the scattering function. Okay. Once I can write, so given any scattering environment, I can find the asymptotic normalized capacity for that scattering environment. That's what this lets me do. Okay, here's another interesting thing about this result. So I didn't make any assumption about the joint distribution of the elements. Right? It could be non-Gaussian. Okay, and the capacities in general depends on the intricate structure of that joint distribution. Asymptotic capacity, on the other hand, depends only on the second order statistics, only the scattering function. So asymptotically, you basically you can throw away the information about the joint distribution, the details, and just keep the variances. And that's interesting.
Could you get this directly?
No, you couldn't. If you look at it in a finite case, it could be dependent on the.
No, I understand that, but couldn't you, in the sense that if n gets large, somehow every user, with respect to the rest, there must be some form of averaging taking place.
That's kind of happening in Gurko's result. I mean, there are no users here; they're antennas.
Right.
And basically, yes, in Gurko's result basically it says that I can write down the limiting eigenvalue distribution for this without really knowing anything about the variances. And so that means there's some kind of central limit theorem going on within this. That's what is giving me.
Question: would that n is equal to nr go to infinity together?
Yeah.
What if they went to infinity at different orders? Oh, is it very different? Can you get very different results?
You could, yeah. You could get different results. And again, in practice, these results would be useless if they were not good for a few antennas. And we'll see now that even for 3 or 4 antennas, that you have good results. In that case, it doesn't matter whether it's okay to look at them going in the same way. Okay. So let's get to some results. So here's a scattering function. This is not a very correlated environment because it doesn't have many zeros, and this is roughly an IID channel, but not quite. And so we know for the IID channel, actually from Kamath and Hughes results, that you get very good approximations even for a few antennas for looking at the asymptotics. And that's true here. So even for a 4x4 system, you get something that's you can't really distinguish between the asymptotic approximation and the asymptotic. Okay. So here's another thing that's happening. So as I said, the asymptotics only depend on second order statistics. and the asymptotics are accurate for few antennas. So basically, even for small number of antennas, you can throw away more detailed information in computing the capacity. That's what they can say. And here's a more correlated channel, because there are a lot of zeros. And you can see here now, at high SNRs for a 5x5 system, there is some gap. So it's not significant. Okay. So the asymptotics are quite good even for a small number of antennas. All right. So what do? We exploited this so-called virtual representation, which is an approximation, but we think is a good approximation, to analyze the coherent capacity of MIMO channels. So this allowed us to consider a very general model with channel statistics. Okay. So one of the results is that so one of the things that comes out of this analysis is you don't really need this product form assumption to do analysis. Okay. The optimum input covariance is always diagonal in the virtual domain. That's what we found. And at low enough SNRs, beamforming to one of these virtual angles is optimum. And it actually can be close to optimum even at moderate SNRs. And then we looked at the asymptotic normalized capacity, or the capacity scaling with number of antennas, and we showed that that depends only on second order statistics, and they're accurate even for small number of antennas. Okay. One comment before I get your question. So, a restriction that we have made is that we have a uniform linear array at both ends. Okay. If you don't have a uniform linear array, you won't have this Fourier representation anymore, and then you can't use a fixed set of bases at the transmitter and receiver to get your virtual representation. And then things get a lot more complicated. Okay. I think if you consider more general array geometries, and which might be the case when you have small antenna, patch antennas sitting on laptops and stuff like that, it might be hard to actually have uniform linear arrays. Then you can do an analysis similar to this, but it's not going to have the simplicity.
Thank you very much. There's a paper on this on my website. It's still not. It's still. I guess we just revised it in October, so the latest version is on the website. It has the details of the line of sight component stuff through it and so on. Any questions? I had one. The correlation between the elements of H do not become significant as n becomes large, in fact, like you said.
No. It's the statistics. The details of the statistics don't become important. The correlation is still important.
But the variances come in the formula.
Only the variances turn out to be important.
So
of the virtual coefficients.
Of the virtual coefficients.
Yeah.
So if you compare this with the case where the transmitter is allowed to know H as well, does that final answer coincide with it in that particular case, or is it different, or is it less?
If the transmitter knows H, then
you'd be operating in parallel channels, right? And the variances would be the only things that matter.
Yeah.
Is the final answer close to that? So is that what is happening here?
No, because you can do a lot more, right, when you know H of the transmitter. Not just statistics. Here unless it's. It again really depends on how correlated your environment is. So I think the answer to that is if there is really one angle that dominates and dominates all the others, then you're going to be putting all your power in that angle anyway, and so it shouldn't matter then whether you know the channel at the transmitter or not. I guess that's a good question. So in that scenario, when beamforming is optimum, I guess you don't need to know anything more about it. Even knowing the channel at the transmitter, you couldn't do any better than that, because you would put all your power in that direction. So, no, I take that back.
So that's
I take that back. It's not necessarily true, because it's varying. So even if statistically that's the most dominant angle, Right? There may be some other angles that pop up once in a while and disappear. So it's hard unless there is really no other angle. I mean, there are no scatterers except in one cone. Then
Yeah, then of course.
Then of course.
Questions? More questions? Yeah. Yeah, let's start with you.
Good morning. My name is Afosa Edinburgh. I need to find out what the greatest advantage of beamforming would be at this point, because I noticed you mentioned that low SNR.
Low SNR and correlated environments. So I would say in outdoor environments where you have scattering from a few, let's say in a suburban kind of environment, where you may have scattering from just a few localized angles, then you basically send all your power in those directions and not worry about doing space-time coding. And so I think it needs to be re-examined. I mean, for indoor environments when you have very rich scattering, then it might be useful to actually send power in all directions and get your multiplexing gains. But if for correlated environments at low SNRs, you may not want to do anything more than just beamforming. Just finding the right angle all the time. Maybe it's more than one angle, but it's still a one-dimensional signal. So you just set your coefficients to basically send power in the right directions and do that.
So this is one of the few instances where low SNR is acceptable.
Yeah, and low SNR doesn't have to be very low. In my example there, 5 dB was, per receiver antenna, 5 dB is actually quite high in any real environment. So that's the point I was trying to make in that example.
Yeah.
I didn't understand why the asymptotic capacity as the number of antennas goes to infinity matches so well with the capacity for a small number of antennas. I mean, is there a reason behind that? Is there something in the model that allows that?
Well, it won't match as well when you make it very correlated. That's true. But basically, you are making use of, somehow you're looking at statistics when you have lots of random variables adding up in some form. And if you have, I guess, good statistics to begin with, you don't have to wait as long to get there. Actually, that's a good question. The reason why that's a very good question is that in the examples, I actually assumed, the examples that I showed you, the numerical examples, the statistics were assumed to be Gaussian in computing the exact capacity. And so basically, in that case, in the Gaussian case, you already have good statistics to begin with, and may not take as many antennas to get to the right answer. So if we had something that was very non-Gaussian, you might have a larger gap for smaller antennas.
Yeah, question?
I want to ask you, when you compute the exact expression, do you still have the approximation that the component of edge wiggle is independent? I mean, they are independent.
Yeah.
And how good is that?
Of edge still. Components of edge still.
And how good is that approximation if you have only small number of antennas? I want to ask two aspects. First, how good is the independent assumption? And second, is that sensitive to that if you change the antenna angle a little bit?
Well, the independent assumption is going to be better for a larger number of antennas, but it's actually, it was shown in some results by this Austrian group, Bonek and others, that even for 4 or 5 antennas is not a bad approximation. So I think I really think it's better than the Gaussian product form correlation model.
Well, basically, what I understand what you're doing here is basically do certain kind of discrete type Fourier transform in the space domain. Basically, you assume the things you've got the spectral domain is independent. So I guess that will depend on how discrete it is.
Yeah. And basically, if you have stationarity in the spatial domain, this will be a good approximation. And you get essentially you're getting stationarity by making the assumption that the phases are independent and random.
Thank you. There is a roundtable discussion at 2 o'clock. Anyway, Ms. Tianwen, you should. It's downstairs in the CSACN library. You're welcome. And let's thank the speaker again for nice.